Okay, so today I'm going to be talking about blocks in Ruby. Now, before I go there, let me just tell you a little bit about myself. So, as mentioned, I come from Cape Town in South Africa. And I'd like to take this opportunity to thank the organizers for having me here all the way from halfway across the world. So this is what Cape Town and Table Mountain looks like according to the internet. Well, as seen from a helicopter, that is. So here's a more realistic view. This is a picture I took from a beach that's about 25 minutes outside the center of Cape Town over there. And the picture's quite fuzzy, but as you can see, it's still quite beautiful. An interesting fact about Cape Town at the moment is that we quite literally almost ran out of water earlier this year. So this is what our biggest dam looks like at the moment. And as you can see, there's hardly any water in it. And essentially what happened is because of climate change or some other reason that you might want to blame, we've had a lot less rainfall over the last couple of years than what is normal. And the dams all started running lower and lower until most of them looked like this. Now, fortunately, all the Cape Townians woke up at the very last minute and started saving water at quite an astonishing rate. And so we managed to avert the crisis that would have been running out of water for now. An unfortunate consequence of this, however, was that all the tourists ran away. But what I'm saying is that there really seems to be no risk of us running out of water anymore this year. And so you all can come back now. Okay, so an interesting fact about me is I also have a cat. Her name is Emma, and she's quite adorable, as you can see. Unfortunately, unlike Max's cat, there's no way in hell she's ever going to play catch with me. But she does know one neat trick, and that is to sit on my keyboard whenever I'm trying to do any work, as is demonstrated here, here, and also here. Okay, so that's enough small talk for now. So as I said, today I'll be speaking about blocks in Ruby. Now, as you probably know, you can do some pretty interesting things with blocks. For example, you can do what I've got here, which is defining a variable outside the scope of a block, and then you can use it inside a block that you pass to a method without any issues. Now, I recently ran into a situation in my code where this scenario seemed to stop working, and my code looks something like this. It was an RSpec example, and in this example, I had a let block that defines something called test index. And then inside my it block, I was creating two nested blocks. And so the first block was being created and passed to class eval, and the second block was being created inside that and passed to a method called model. And it was inside the second nested block that I was trying to use test index. Now, based on the example I just showed you, I thought this would just work. However, when I ran it, I got RSpec or Ruby complaining about an undefined local variable or method test index. And what was even weirder was I found that after playing around with the code a little bit, that this slight modification that I made to the code, where I defined a local variable myIndex inside the it block, and then assigned test index to that, and then used myIndex inside these two nested blocks instead of test index, the RSpec example would pass without a hitch. Now, in order to try and figure out what was going on here, I came up with the following differential diagnosis. And the first theory was maybe the problem is that you can't actually use a variable defined outside the scope of nested blocks over here inside the innermost nested block. So I thought maybe the problem was because they were basically just too many blocks, and I was defining test index way outside all of them. You just can't do that. But I quickly came up with an example showing that this seems to work just fine in general. So over here you see I'm defining my string variable again and using it inside two nested calls 2 times without an issue, and I'm sure you're not surprised to see that. So theory number 2 was maybe the problem is that I'm using let to define test index. So I did a little bit of digging, and I found the following bit of RSpec documentation that says that actually let defines a memoized helper method and not a variable as I first thought. And so I thought maybe the problem is that you can't actually use a method defined outside the scope of a block inside a block. And again, I quickly came up with an example, however, that shows that this seems to work in general as well. So here I'm basically just defining string as a method and again, using it inside my block that I'm passing 2 times, and we all know this works. And so my final theory was that maybe, just like some other things in this world, the problem was that maybe RSpec is just a bit crap. And so maybe there's there is a problem in RSpec, or there's some bug in the RSpec code that's making my example fail when it should have been passing. But again, it didn't take me long to come up with a simple example showing that this seems to work out in general as well. And so I didn't even bother to pursue this avenue of thought any further. Now, at this point, I realized if I was going to understand what was going on in my RSpec example, I needed to understand the underlying mechanisms of what makes blocks so powerful in Ruby better. And so the first question we can ask, of course, is, what is a block really? Well, it turns out that a block is Ruby's implementation of Sussman and Steele's closure. And that is essentially defined as just a combination of the 2 following things. It consists of a Lambda expression, which is just a function that takes a set of arguments. And then it also consists of an environment to be used when calling that function. Now, obviously, for blocks, this environment is going to have to include the surrounding scope in order for my previous examples to work. Okay, in the underlying C code for Ruby, the block is actually an object, and it's called RB_block. In Ruby 2.2 and lower, it is actually called RB_block, and it's got an _t at the end as well. And it has several properties. Among those is the isec pointer, and this is just a pointer to the Lambda expression of the closure. Then it has an environment pointer property as well. And this is a pointer to the surrounding stack frame of the block. In other words, it's going to point to where all the local variables of the currently executing method inside which you're creating the block is located. And it's this environment pointer that is the reason that you can use variables defined outside the scope of your block inside your block. And I'll show you how that works in a minute. Now, in Ruby, any code you execute is always going to be executing inside some other method. And so it will always have a surrounding stack frame. So even if you think about it, if you're executing code in your console, that code is executing inside the eval method and will also have a surrounding stack frame. And so in a lot of the examples I'll show you in the following slides, I'll often show you the method surrounding the code that I'm busy looking at so that I can show you that surrounding stack frame. Now back to this environment pointer. It turns out Ruby uses this to do some very interesting things on the stack. And to show you what I mean, let's first take a look at what happens during a normal method call in Ruby. So the method call we're going to be looking at is this display strings method. You can see it's very simple. It's got 2 local variables defined inside it, and it essentially just outputs a combination of the 2. And what I want to do now is I want to take a look at what happens on the stack when display strings is called. So when we call it like this, what Ruby does is it creates a stack frame for the display strings method as shown over here. It then pops all the local variables and any arguments passed to the method onto the stack. There's 3 dots here to indicate some other housework that needs to happen, which isn't important right now. This SP, by the way, is just the stack pointer. And then Ruby also creates a special slot in the stack frame. Now, this special slot is used to keep track of whether a block was passed when we call our method. And if you think about it, when you call a method with a block in Ruby, you're essentially just passing that block as an argument to the method call. And so the fact that it gets its own slot on the stack frame kind of makes sense. In this particular example, though, you'll see we are not actually calling display strings with a block. And so the special slot is going to remain empty. But what Ruby does do is it sets its own environment pointer to point to the special slot in the stack frame. Now, this environment pointer is related to, but slightly different from the one I had on this screen when I spoke about blocks. So this environment pointer property over here is specific to the block. And as we'll see in a minute, it actually gets the value of Ruby's current environment pointer. But that value then is static, and it gets saved down for the block, and it's not going to change for as long as the block exists. This environment pointer here is Ruby's environment pointer, And that changes as your program executes and as whichever method is busy executing changes. Right, so this is everything that happens during a normal method call in Ruby. So let's take a look now what happens on the stack when we call a method with a block. So the method call I'm going to be looking at is this one over here. You'll see I made a small modification to the display strings method in that I've got a call to times inside it, which you see takes a block, and that uses the two local variables inside it. So just to be clear, the method call on the stack I'm going to be looking at now is this call to times, which takes a block. So here is the stack as we had it before while display strings was busy executing. So again, we pop the local variables onto the stack. Here's the special slot. Stack pointer has been set, and Ruby's environment pointer has also been set. So this is everything we had before. Now this method is busy executing, and Ruby gets to the point where the times method needs to run. This is another method call. So what happens is a new stack frame gets created for that method call over here. Again, there's all the space for the local variables, etc. It, of course, also has a special slot. But this time, we're calling times with a block. And so what happens now is that Ruby creates the block object on the heap. Now remember, the block is an object in Ruby, and so it goes on the heap because that's where objects go. There's also something interesting about this, which was pointed out to me recently, in that in Ruby 2.2, this block gets allocated on the heap when it's passed as an argument. In Ruby 2.3 upwards, there's been an optimization, and it looks like to me that, in fact, the space doesn't get allocated on the heap until the block gets accessed for the first time. So that's a slight difference between those versions. Either way, once the block has been created, the value of Ruby's current environment pointer gets copied into the environment pointer property of this block, and the special slot gets set to point to this block on the heap. Okay, so that's passing block as argument done. Now time starts executing. And as soon as the yield statement gets hit, the block code needs to execute. And what Ruby does to execute block code is it creates another stack frame on the stack for the block. It does all the usual things, such as popping local variables, arguments, etc., into that stack frame. And this stack frame also has a special slot, and Ruby adjusts its environment pointer to point to this special slot of the block now. Now you'll notice when I did that, I didn't actually delete the old environment pointer. I renamed it to previous EP. And the reason I did that was because in the background, Ruby creates a kind of ladder of environment pointers, as you see here. And that gets used every time you try and access a local variable defined outside the scope of your block, and maybe even in surrounding scopes that are nested around your block, inside your block. And essentially it does that by starting at the block's environment pointer property in this ladder, and it travels down this ladder looking for the local variables you're trying to access. Now I've kind of simplified the process a little bit. There's quite a lot more that needs to happen, such as various block properties needing to be copied from the heap onto the stack frame of the block. But that isn't important right now. The point is that it's this ladder of environment pointers that allows you to access local variables defined in the scopes around your block, inside your block. And this is called dynamic variable access, by the way. Okay. So this explains why we can access local variables that were defined outside our blocks inside our block. But why can we access methods defined outside of our blocks inside our block? In other words, why does this bit of code here work, where basically we're defining the method string and then using it inside our block? This can't work by the same mechanism, because if it did, then my initial RSpec example, which defined the test index helper method and then used it inside nested blocks, probably would have passed. But we know it fails. And to understand how this works, we need to take a look at the Ruby block object again. So here it is with its RSec and environment pointers. And it turns out this block object has another really important property called the self property. And this self property gets set to whatever object was active when the block was created. So you can see it really as pointing to whichever method was, or the owner of whatever method was busy executing when the block was created. You can see it as getting the value of whatever self was when the block was created. But the point is that it's a self property that allows us to access methods and values of the object that was active when the block was created inside the block. And I can show you the self property in action in some live code. So what I'm doing here is I am defining the block tester class. And as you can see, hopefully, as you can see, it's a really simple class. It's got the block func method defined in it, and it essentially just yields to whatever block you pass it. And now I'm going to define my block, my class, which is another class. And you can see, in particular, it's got this test func method, which is of interest. And what we're doing there is we are defining a new block tester instance, and then we are calling block func on that block tester instance, and we're returning self from inside that block, because the point is I want to see what self is going to be pointing to in this block, and this self will actually be the return value of test func. Now, when I look at this code, I kind of intuitively almost want to say that self is going to be test object, because that's what it looks like to me. But let's take a look at what the actual value is by running this code. So first, I'm just going to create an instance of my class. That gives us that. And now I'm going to call test func on that instance. And you can see the value that was returned by that method is, in fact, our original instance of my class. In other words, what this is saying is that self in this block is actually pointing to the owner of test func, which is our instance of my class. And that is consistent with what I said before. What's interesting about this is that we also know we can intuitively actually call method 1 inside this block. And it turns out the reason we can do that is because this self property over here is actually pointing to the owner of test func, which is our instance of my class, and then obviously has method 1 defined on it. Okay, now given everything I just said, I kind of would have thought, hold on. I kind of would have thought my original RSpec example should have passed, because here I'm defining test index, and we now know that's a helper method. And you'd think RSpec would be smart enough to add this method to whatever RSpec object is active inside this it block. And that should mean that inside this first block, the self property is going to point to that RSpec object, which means the self property inside the second block should also point to that RSpec object, which has test index defined on it. And therefore, the code should work. But we know it doesn't. And when we take a closer look at this bit of code over here, what's happened? We see that actually the first block is being created and passed to a method called class eval. Now, I know none of you were there, but about a year or two ago, I gave a talk on eigenclasses. And in that talk, I had this slide where I went on and on about how important it always is to keep track of what self is going to be inside the block when one calls class or instance eval on an object. And what I said was that for class eval, self will always be set to the class of the receiver inside the block. And in other words, what this slide is saying is that class eval is different from normal methods that take blocks, because self inside the block for class eval will not be set to point to the currently active object. It's going to be set to point to the class of the receiver. And so in this slide, what this means is that self inside the first block is going to be pointing to the class of QuattroPage. And that means self inside the second block is also going to be pointing to the class of QuattroPage. And I'm guessing there's no method called testIndex defined on that class. And you can see there's also no local variables by that name anywhere in scope, and that explains why this example failed. So yeah, this is a little bit embarrassing considering all the hopping on I did on the topic a year ago. But I think what everything I just said also explains is why this modification that I made to my RSpec example made it pass. Because if you recall, what I did is I created a local variable and assigned the test index to that. And we now know that it's via the environment pointer ladder that this inner block has access to any local variables in the surrounding scope of that block. And that explains why this example passed when I made this small modification and used the local variable instead of the test index method. Okay, so that's all I'm going to say about this RSpec example today. It's time now to move on to a use of blocks in the Ruby programming language, which really lends some elegance to the language, I believe, and that is its use in define method. Now, you may or may not know that there are two main ways in which to define methods, or define instance methods, at least in Ruby. The first way is to use the def keywords, as is done in the first paragraph, and the second is to use define method, as is done in the second. Now, the difference is that whereas the second paragraph actually works, the first one does not. And the reason the first paragraph doesn't work is because def is what they call a scope gate in Ruby. Now, essentially what that means is whenever you use def, you're going to lose access to all the local variables defined in the surrounding scope. And so when you run the method defined in this way, Ruby is never going to be able to find string 1 or string 2, and the method call is going to fail. However, you'll notice that define method takes a block. And actually what it does is it defines the display strings instance method in such a way that it actually runs the block code every time display strings is called. And we now know it's via the environment pointer ladder that this block has access to any variables defined in the surrounding scope, which means display strings defined in this way will be able to find string 1 and string 2 and will execute fine when you run it. Now, you may ask, given its relative elegance, why not just always use define method and forget about the def keyword completely? Well, it turns out that creating a block and running it does not come without its overhead. So you may recall this slide that I had where I showed what happened when you called a method with a block. We needed to create the block object on the heap, copy the environment pointer value into its environment pointer property, set the special slot to point to the object on the heap, and then every single time yield was hit, we needed to create a new stack frame, stack pointer needed to move, environment pointer needed to be adjusted to point to the special slot, the old environment pointer value needed to be saved down to create this kind of ladder, and there was other housework that needed doing as well, such as various properties on the heap in the block object needing to be copied to the stack frame. And everything I just said, more or less summarized in this gray block, needs to happen every single time yield is called. In this particular example, it needs to happen 10 times. But as you know, this could need to happen hundreds or even thousands of times. And so yes, blocks, when they run, can be pretty slow. And it's because of its use of blocks that any method defined using define instance method is going to be quite slow when it runs. And as you'll see in a minute when you speak about lambdas, you'll see that they can be quite expensive in terms of their memory use as well. Now you may ask, how slow exactly are blocks? Well, we can check this in our code again. So here I'm going to benchmark two loops. The first one, as you can see, is a simple while loop. It iterates 10,000 times and adds 1 and 1 together. And we see that that takes roughly that amount of time to do. And now I'm going to benchmark exactly the same thing, but this time I'm passing a block to times instead. And the difference isn't that obvious. It depends. Testing things this way is a little bit sort of volatile. But in most cases of me trying this, the general result seems to be that actually running the code using a block and passing that to times is more or less twice as slow as doing exactly the same thing using a while loop in Ruby. And so it's obviously, if you care about the speed of your code, and obviously in Ruby on Rails applications, we often don't, but if you do care about the speed of your code, it's probably wise to try and avoid the use of blocks as much as possible. Okay, so I mentioned lambdas just now. Well, what is a lambda if not just a block as a data value? So here's a very simple example of a lambda being created in case you never saw that before. You see we pass it a block, and I'm using some of the local variables in that block, and here I'm doing a simple call on that lambda. I think this code makes it quite obvious that a lambda is also an object in the underlying C code for Ruby. The object looks something like this. It is called rb_proc_t. It quite predictably has a block property with all the usual things inside it. And then as an interesting side note, it's also got a property called isLambda. And this property gets set to true when you're creating a lambda, and it gets set to false when you're creating a proc using the proc keyword instead. And that's the main difference between a lambda and a proc in the underlying C code for Ruby. Who would have thought? And then besides these, there are also some other properties, such as the enval property, which we will see in action in a minute. Now, lambdas are blocks as data values, so they are pretty cool. It turns out that they are, in fact, even cooler, as demonstrated by this bit of code over here. So display strings func, as you can see, is a simple method. It's got two local variables. But what it does then is it creates a lambda that takes the block that uses those variables, and then this lambda is returned as the return value. And as you can see, we call this function, we assign the lambda to func value, and then we do a call. And this bit of code works. And if you know anything about how stacks work, you'll know that the fact that this line of code actually works is quite amazing. Now, to show you what I mean, let's take a look at what happens on the stack during this method call. So here's the usual stack frame for display strings func. String 1 and string 2 local variables are on there. Environment pointer set, stack pointer set. Now, Ruby gets the line of code where the lambda needs to be created and returned. And so what happens now is that created lambda is assigned to the func value variable on the stack. But you notice when I did that, when this method exited, the entire stack frame for this method was wiped off the stack, along with all references to string 1 and string 2 local variables. That means there are no longer any references on the stack to the string 1 and string 2 objects on the heap, which means they will be garbage collected and can no longer remain available to your program. And yet, as I said, this line of code here works perfectly, and it actually prints out the values for those local variables. So how can this be? Now, to see how this can be, we need to take a look again at what happens on the stack and heap, firstly, when we create a lambda, and secondly, when we execute it. So here is what the stack looks like as I had it just now. So this is while display strings func is executing. Then we have the local variables there. Stack and environment pointer have been set. Now this guy executes, and it reaches a point where it needs to create the lambda. And it turns out that what Ruby does when it creates a lambda is it creates a copy of the entire surrounding stack frame for that lambda, and it puts it on the heap. Now, this copy of the stack frame has a wrapper object around it, as I'm showing here, but that's not important, so I'm leaving it off the diagram for simplicity. And once this copy of the stack frame has been created on the heap, Ruby can now create the lambda. So here's the lambda on the heap. It's got its block property inside it. You'll see its enval property is actually set to point to this copy of the stack frame on the heap. And once all of this is done, this is quite interesting, is what Ruby does now is it resets the current environment pointer to point to this copy of the stack frame on the heap. Now, this is quite an interesting situation because usually this environment pointer points to a location on the stack, but now it's pointing to a location on the heap. And once this is done, it's this modified value for the environment pointer that gets copied into the environment pointer property of this block that belongs to the lambda. And this lambda is now set, it can be returned. And so display strings func exits, and the lambda is assigned to the func value variable on the stack. Now you'll notice what we have now is we've got a pointer going from the stack through this lambda object on the heap to this copy of the stack frame on the heap, which has references to the string 1 and string 2 variables. And so there's a live pointer going from the stack to somehow to the string 1 and string 2 objects on the heap somewhere, which means that they won't be garbage collected and they can remain available to your program. And that explains why the Lambda can print out the values for these variables long after the stack frame over here got wiped off the stack. So that's everything that happens when the Lambda is created. Now let's see what happens when it gets called. Well, all that happens is the block code needs to execute. And so we know that when block code executes, a new stack frame is created for the block. So here it is. And the environment pointer gets adjusted to point to the special slot of this stack frame. And this copy of the stack frame on the heap is now going to be used as the direct environment in which to execute the block code. Now, you'll notice this means Lambdas can be quite expensive in terms of their memory use, because as you can see, this copy of the stack frame needs to remain on the heap for as long as the Lambda exists in your program. And you'll notice that any variables that actually had references in this copy of the stack frame will also remain on the heap for as long as your Lambda exists in your program. And so if you're not careful what you're doing, your Lambda can unintentionally cause your program to use a lot more memory. Obviously, also, the more Lambdas you create, the more expensive your program can become in terms of its memory use. But Ruby has found a way to mitigate this to some extent, in that if you're creating several Lambdas in the same environment, Ruby is not going to create multiple copies of the stack frame. It's rather going to use the same copy of the stack frame on the heap. And it essentially does that by checking whether the environment pointer already points to a location on the heap rather than to a location on the stack. Okay, so I know the longer you look at this diagram, the more you kind of feel like you've seen it before. But I think the point of this diagram is that when the Lambda is created, there is a copy of the surrounding stack frame created on the heap. And when the Lambda is called, it's this copy of the stack frame on the heap that is used as the direct environment in which to execute the block code. Right, so you remember that I mentioned there's a wrapper object around this copy of the stack frame. Turns out we've got access to this wrapper object via the binding class. And so I can show you how to get access to that with a simple method over here. So you'll see what I'm doing is I've defined get environment, and essentially just I've got two local variables inside this method, and I'm returning binding from inside that. And now what I can do is I can get a handle on that binding object, as you see over here. And then we can go and poke around inside it a bit. And you can see that quite predictably, it's got two local variables, x and y, defined. And it's got the values that get environment had for x and y when we defined it way up here somewhere, over here. And the interesting thing about this binding object now is that we can actually use it in our code. So for example, what we can do is we can pass it to eval, and we can say to eval, execute this expression x plus y, but use the binding object that I've passed as the environment in which to execute the expression. And you'll see that it works fine, and it prints out the value 3, even though there's no local variable x or y defined in the local environment. What's interesting about this call to eval is that it's essentially creating a closure, because it consists of an expression and also of an environment in which to execute that expression, and that's exactly the definition of a closure. Okay, so finally, I mentioned that Lambdas were relevant when talking about the find method. Well, to see what I mean, let's just take a look at this example over here. In particular, let's just focus on this define method call. So you'll see that it takes a block, as I said before, and actually what the find method does is it creates this display strings instance method to be a Lambda. And so what this means, obviously, is that creating this instance method and executing it is going to be quite slow, because as you can see, there's quite a lot of overhead involved in creating and executing a Lambda. Again, you may ask, how slow exactly is the find method? Well, we can do some more benchmarking. So what I'm going to do is I'm going to define two methods. The first one, using the def keyword, and I'm going to benchmark how long it actually takes to create that method and hope it works. So there I've defined my first method, and now I'm going to define a second method that does exactly the same thing, but I'm using the find method to create it instead of the def keyword. And you can see that takes roughly that amount of time, and if we print them out in a sort of more readable format, we see that the demo gods are against me today, so let's try it again. So at the moment, it seems to be only taking 1.5 times as long to create the method using the find method as opposed to using the def keyword. But often enough, it seems to be it can take up to more than twice as long to use the find method. And now let's see how they compare when we execute them. So here I'm benchmarking, calling method 1, the first method, 10,000 times. You see it takes that amount of time. And now I'm calling the second method 10,000 times. Remember, this was created using the find method instead. And we see, again, it takes almost twice as long to execute exactly the same method, but rather it was defined using the find method instead of the def keyword. So there's a significant performance implication. So yes, the method is slow when you create it using the find method, but what it does do is it allows this bit of code over here to work, because you'll notice what has happened is we've again got a method with local variables, which are then used inside this block. But we now know that once the find instance method exits, string 1 and string 2 will be wiped off the stack and will theoretically not be available to this instance method anymore. But because this instance method has been created to be a Lambda, we now know that there's a copy of the stack frame that has been created on the heap, and hence this instance method over here will be able to find string 1 and string 2 long after the find instance method has exited. And that's quite a good thing, because instance methods do tend to stick around for the duration of our programs. Okay, and that's all I've really got to say today. Here are my details. I'm CodeKitten on Twitter, EP De Jager on GitHub. A lot of the more technical explanations I gave today came out of this very awesome book called Ruby Under a Microscope. And I work for a company called Zappystore, which does some pretty awesome market research software using Ruby and blocks extensively. Thanks very much.